Okay, so we're going to do question 9.8. So this question is basically justify the marginal utility of constant elasticity of substitution utility function. So it's pretty straightforward. The function is a little bit more complicated than what we did in the previous exercise, but the principle is exactly the same. Okay. So this is just a partial derivative where you differentiate a utility function with respect to one variable, treating the other variable as constant. Alright, so we are given a CES utility function, utility as a function of x and y equal to theta x to the power a plus 1 minus theta y to the power a and everything to the power rho on a. Okay, so this is when a is smaller or equal to 1 and difference from 0, or it's going to be equal to x to the power of rho times theta y to the power of rho 1 minus theta. Okay, if a equal to 0. Okay, so question 9.8 is just asking you to just find the marginal utility of root x and marginal utility of root y for the case of a smaller or equal to 1. Okay, so what we do is we just have to differentiate the utility function. So right, so marginal utility of x is just going to be the differential of the utility function with respect to x. Okay, so if I'm differentiating the first utility function first, okay, for the case where a is different from 0, so this is the case where a is different from 0. Okay, both of these are when a is smaller or equal to 1. Okay, but the first case where a is different from 0. So if I differentiate the first expression over here with respect to x, then the first thing you can see is we have to apply the chain rule over here because we have a function inside a function. Okay, so what I'll do is, okay, so I got a utility equal, so when a is different from 0, the utility is theta x to the power a, 1 minus theta y to the power a, and everything to the power rho on a. So now if I let the whole thing inside the bracket be a function of x and y, okay, so it's just going to be equal to psi z function as a function of x and y. Okay, so the whole thing inside a bracket. So what we have over here is going to be u equal to z to the power of rho on a. Okay, so therefore the differential, so marginal utility of x will just be equal to differential of the utility function with respect to x, and that will just be the differential of the utility function with respect to z, okay, multiplied by the change in z given the change in x. Okay, so we got this is basically the chain rule. Okay, so so first of all, I differentiate utility function with respect to z. Okay, so given that a utility function over here is just as a function of z, it's just going to be equal to z to the power of rho on a. Okay, so this is basically a short form. So if you differentiate with respect to z, you get rho on a, okay, z rho on a minus 1, okay, and multiplied by differential of z with respect to x, and z is just the whole thing inside over here. Okay, so when you differentiate that with respect to x, you get theta is still theta, okay, which is just a constant. The differential of x to the power a is just a x to the power a minus 1, which is a power rule. Now 1 plus theta times y to the power a is basically just a constant, the whole thing, because it doesn't have any x in it. Okay, so when you differentiate a constant, you get 0, which is a constant rule. Okay, so this will just give you, so a over here will just cancel with a over here. So what I'm left with is rho times theta, okay, times z rho to on a minus 1 times x a minus 1. Okay. Okay, so now as you can see, we have a z over here, and we want to express that in terms of utility, in terms of u, okay, because that is what the question asking you to do. So we want to express this expression, okay, in terms of u. So what we want to do is we want to convert z into u. So knowing that u is equal to z to the power rho on a, then in order to find the value of z in terms of u, you just have to take the power of a on rho to both sides of this equation. Okay, so I'll set as u equal to z to the power rho on a. Then, so therefore, if you take the power of a on rho to both sides of this equation, you get u to the power a on rho, and it's z to the power rho on a, everything to the power a on rho. And so, as you can see, this will just basically give you z to the power 1, okay? And that will just be equal to z. Okay, so the rule over here, if anyone is not familiar with the power, is x to the power a, everything to the power b is equal to x to the power a times b, okay? So that's the rule. So therefore, z to the power rho on a, everything to the power a on rho, it's just going to be equal to z to the power rho on a times a on rho, and that will just give you 1, okay? Alright, so we got z in terms of u, then we just have to substitute that into our marginal utility function. So I got marginal utility of x equal to rho times theta, and z is u to the power rho, sorry, a on rho. Okay, and that is z, and I want everything to the power of rho on a minus 1 times x a minus 1. Okay, now I basically got the right thing. I just have to play around with it and try to rearrange it to make it the form that the question is asking you to show. Okay, so again, I got the power to the power, so I just apply my power rule over here. So I got rho times theta, and I got u over here. Now it's just going to be a on rho times rho on a minus 1, okay, and I want to move x to the denominator just as in the expression in the textbook. So if I want to move it to the denominator, then I just have to put a negative sign in front of it, so that it's just become x to the power 1 minus a, okay? So that will just give me rho theta utility. So if I expand the bracket, I got a on rho times rho on a, which is give me 1 minus a on rho, okay, which is and everything divided by x to the power 1 minus a. Okay, so I got rho theta utility of 1 minus a on row is just basically if you take a common denominator, it would just be row minus a, everything divided by row. Okay, and divided by x to the power 1 minus a. So if you're looking at this, it is just exactly the expression that we meant to prove, okay, which is right. Okay, so very similar for the marginal utility of y. That would just be basically the differential of u with respect to z and times the differential of z with respect to y. Okay, so again, this is the chain rule, and the differential of u with respect to z, it's just going to be the same over here, so which is rho on a. Okay, times z to the power rho on a minus 1, and then we multiply by the differential of z with respect to y. So if I differentiate this z with respect to y, then I'm treating x as constant, so the whole thing in front over here is going to be 0, and what I'm left with is 1 minus theta. Okay, a y to the power a minus 1. Is that right? Okay, that's right. Okay, so again, a would just cancel with a over here, so what I'm left with is just going to be rho 1 minus theta z to the power rho on a minus 1 times y to the power a minus 1. Again, we want to express this in terms of utility function, and we just got exactly the same z as before, so I got rho 1 minus theta, and my z is just equal to u to the power a on rho. Okay, and everything I want to the power of rho on a minus 1 times y to the power a minus 1. Okay, and so therefore again I just have to expand, use the power rule here. I got u to the power a on rho times rho on a minus 1 a y to the power a minus 1. Okay, so I got rho 1 minus theta u to the power, if I expand the bracket, I get 1 minus a on rho. And I want to move y to the denominator, so that will just become y to the power 1 minus a, just like before. Okay, so I got rho 1 minus theta u, if I use a common denominator over here, which is rho minus a, everything divided by rho. So sorry, that's the power, so I should make it clear. So utility to the power of rho minus a on rho, and everything divided by y to the power 1 minus a. Okay, so that is the expression that the question asking you to prove. Okay, so that's the case where a is different from 0. Now the second case is where a equal to 0. Then your utility function is going to be equal to x to the power rho theta y to the power rho 1 minus theta. Okay, so if I, again, to find a marginal utility, in this case, it's just the differential of u with respect to x. And this is basically a straightforward case because we do not have a chain rule over here anymore. So this is just basically treating y as constant, so the whole thing will remain the same. So I got y rho 1 minus theta. Okay, so it's remain the same there, and if I differentiate x to the power rho on theta, I get rho theta x to the power rho theta minus 1. Okay, and I just want to express that in terms of the utility function. Okay, so I got utility function over here. It's just x times y. Okay, so I just got y to the power rho 1 minus theta times, so if I move theta and rho to the front, so I got rho theta y to the power rho 1 minus theta x to the power rho theta, okay, and everything divided, and this is divided by x, because I got x to the power rho theta minus 1, that is just equal to this. Okay, now why am I doing this? Because I just want to express this in terms of utility function. Okay, so as you can see, the thing over here, this expression over here is basically the utility function. Okay, so what I got is rho theta utility of x and y, okay, and divided by x. Okay, so as you can see, this is just the expression in the common, in the general form, because when I equal to 0, if you substitute that into the expression that the question asking you to prove, then it's just basically exactly the same as this. Okay, so okay, so as you can see, okay, so the general expression is where marginal utility of x equal to rho theta utility of x and y to the power of rho minus a on rho, and everything divided by x to the power of 1 minus a. Okay, and if a equal to 0, then this marginal utility of x is just going to be equal to rho theta. Now if a equal to 0, then this becomes utility of x and y power rho divided by rho, which is 1. Okay, and x1 minus 0, which is going to be x, and this is just exactly the same as the expression we got over here when we differentiate our utility function here. Okay, so that is just right. Okay, so very similar for marginal utility of y, which is differentiate the utility function with respect to y, and so we're treating x as constant, so we got x to the power of rho theta remain the same, and y, we differentiate y with respect to y, we get rho 1 minus theta y rho 1 minus theta minus 1. Okay, so and this is just going to be equal to rho 1 minus theta x rho theta y rho 1 minus theta divided by y. Okay, and as you can see, the expression over here is just the utility function. So I got rho 1 minus theta utility of x and y divided by y. And if you're using the general expression that we found earlier, where the marginal utility of y is equal to rho 1 minus theta utility of x and y to the power of rho minus a divided by rho, and everything divided by y to the power 1 minus a. And if a equal to 0, then again you find that this is just exactly the same as the expression we found by differentiating the special utility function with respect to y. Okay, so I got rho 1 minus theta utility of x and y. This will just become 1 and divided by y, because 1 minus 0 is just 1. Okay, so this is the same as this, which is right. Yeah.